Coming up next on the IP Talk stage, Brian Jeff from ARM, presenting ARM Big Little Processing, saving power through heterogeneous multiprocessing and task context migration.
I'll go ahead and get started right away. The reason we conceived of this technology is we've been getting input from our partners and downstream from OEMs that the mobile market and other markets that are related to it are kind of pushing in two directions simultaneously. We are getting requirements to go faster and faster. More and more performance. You're running very high performance apps, running multiple apps at the same time and switching between them seamlessly. But at the same time, in mobile products and smartphones and tablets, et cetera, we need to be more efficient and last longer on a given quantity of battery life. So we need to have more efficient processors, but at the same time, we need to have higher performance processors to handle the use cases of typical users today. So we're being pushed in two directions simultaneously. That's why we introduced a technology called Big Little Processing. And in this, we've basically set up software so that it can use the right processor for the right job in an instantaneous kind of way. So what we see is that there is a big cluster, a high-performance CPU with 1 to 4 cores, a private L2 cache, and a performance characteristic really defined by the needs of the highest performance apps in the mobile ecosystem. And we've got a small processor that by itself is actually pretty good. It does quite well. It's almost as fast as today's Cortex-A9 processor, but it's very energy efficient. It's been really tuned to be power efficient. And the key is it's got an architecture that matches identically the big processor. So it'll allow you to switch instantaneously between the high-performance CPU and the more power-efficient CPU, taking advantage of a cache-coherent interconnect to allow the transition to be very quick, on the order of 30 or so microseconds or 30,000 cycles in a 1 gigahertz processor. And it allows the software to kind of view this as one processor. So what we find in our benchmarks and our models is this gives an opportunity for about 70% energy savings versus a single processor type. So having big and little together actually offers a pretty significant energy savings opportunity. It's flexible and transparent to applications. So this doesn't introduce new complexity to the user level software at all. It's completely transparent to apps. And it's kind of a best of both worlds solution because it does allow you to push the performance of the high-performance processor up even higher, and it allows you to take advantage of the fact that 95% of the time you can actually be resident on this little cluster or the little CPUs in this cluster and use this only when needed. So it really lets you kind of optimize for performance and power efficiency at the same time. So in terms of the processors themselves, the big core is the Cortex-A15 in this case. It's a very complex, deeply multi-issue, deeply out-of-order pipeline. It gives up to about 5x the performance of today's mainstream high-volume smartphones. If you compare it with the Cortex-A8, with a little bit of a frequency bump from a process node advantage and the microarchitecture improvements we've made since the A8, you're going to see about a 5x performance improvement versus an A8-based handset running at about a gigahertz. So very high performance, big processor. On the little processor, we've gone to a simple in-order 8-stage pipeline. It's really been tuned for power efficiency, but it actually does quite well in performance. Let me bring up some of the benchmarks. So I've got two benchmark suites here. One is kind of a large workload suite that includes things like GCC compilation and ray tracing and big workloads and the like. And I've got another that's a web browser. And what I've done here is I've graphed the little processor, the Cortex-A7, the big processor, which is Cortex-A15 shown in blue, and some of the other ARM-based CPUs on this graph. And so kind of in a relative comparison, what we see is that the big processor gives you a big performance jump over even today's Cortex-A9, which is the defining processor for high-end handsets and tablets today. So it's a pretty big performance jump on the big processor. The little processor actually does quite well. So even though the energy differential is quite significant, the little processor is about 3 times as energy efficient as the big one, what we see is that it does quite well relative to today's high-end. In general, does about 80 to 90% of the performance of a Cortex-A9. So the little processor does quite well for its size. So that's kind of a look at the two in a benchmark comparison. So what we've done here is we've looked at the workloads on a typical smartphone. So we actually took a Galaxy S2 and we instrumented it. We put an application on it. We actually instrumented the kernel itself. So we rooted the phone. We put a monitoring app on there that would keep track of the DVFS state of the processor while the phone was in operation. So this is just a snapshot of one workload. On the coming slides, I'll show you a couple of other workloads that are very common. Things like making phone calls, playing games on the phone, browsing the web, doing file uploads, and those types of activities. And with this monitor, we've been able to track, hey, what is the application's processor doing during this time? And the way I've graphed this, these blue areas, the light blue is where the processor is in standby. The dark blue is where the processor is fully powered off in kind of a power-gated state. And these shades here are the frequency states of the processor. So the red is top frequency state. On this particular phone is a 1.2 gigahertz handset, so this is kind of a 1.2 gigahertz frequency number. This is 1 gigahertz, this is 800. 600 and 400. So you can see, on an existing mobile device, the power management frameworks are aggressively scaling back voltage and frequency, and also shutting off cores as much as possible. This is the first core, this is the second core in the dual core cluster. And what we can see here on this workload is that there's a portion of the time where the processor is really running flat out, but there's a pretty significant portion of the time where it's not doing as much, and there's quite a bit of the time where it's in a standby mode. And so what we can see here is there's an opportunity to use a smaller processor for a portion of the workload. And if I can allocate just this red and orange space to a high performance processor and use a little core to handle all the other stuff, there's a big opportunity for me to save energy. Let's look at this a bit further. How do I put together a big little SoC? Well, from a hardware standpoint, it basically means two clusters of CPUs, a Cortex A15 cluster and a Cortex A7 cluster. So the A15 cluster is the big, and the A7 cluster is the little. Each of them have their own private L2 cache, and they're connected over a cache-coherent interconnect, a piece of fabric that ARM offers, and that our lead partners are taping out with, that basically ties these two CPU clusters together. It allows fully cache-coherent snoops across the cluster so that you can, it enables a very fast migration of context from one CPU to the other. So we don't have to migrate the cache. We don't have to flush and invalidate the cache out of an A7 to wake it up on the A15. We can just migrate a much smaller state and then allow snooping across the cluster when you wake up on the new processor. So that's kind of a key advantage of the approach we're taking with Big Little. We also need a means to distribute interrupts, because if you're migrating a process between a big and a little cluster, you need to be able to handle interrupts and dispatch them appropriately. So we've developed a global interrupt controller called the GIC 400 that is aware of big and little processors and can map an interrupt appropriately based on the run state at any given point in time. So that's kind of the basic hardware. In terms of topology, there's quite a lot of opportunity for differentiation here, and we have partners going in very different directions in terms of topology. On the A15 side, you can put 1 to 4 cores per cluster. On the A7 side, you can put 1 to 4 cores per cluster. We think the big little SoCs that are going to come out first are likely to be 2+2 configurations, so 2 of each, 2 big, 2 little. But we expect there may be things like 2 big cores and 4 little cores coming shortly thereafter. And I'll talk to you in a little bit about the software mechanisms to take advantage of those asymmetric topologies where you might have a different number of big and little cores. And that's what I wanted to talk about next, is the use models from a software standpoint to enable Big Little to work. Because the question I get most often is, how do you know when to switch, and how does a software know where it needs to run? So there are different levels of dealing with that, and I'll kind of step through those here. So the first is a full cluster migration. And these first 2 modes, these migration modes, basically you're taking your running context and switching it back and forth. You're not running, part on an A7, part on an A15. You're kind of switching back and forth based on the demands at a given instant in time. And the way we did this for cluster migration and CPU migration, if you recall, when we were looking at that workload earlier that showed the amount of time a phone spends in different DVFS states, well, the DVFS driver that is making the decisions about when to ramp from a 1.2 gigahertz state to a 1 gigahertz state and down from there, well, that driver, we basically took it and modified the back end and made it aware of an additional set of DVFS states besides these 5. And we said, look,
look at these as one logical set of DVFS states and add 5 to it for the big processor. And so when you reach this point, let's say if you're running on a little and you start ramping up, when you reach this point and your DVFS driver samples the load and determines that you need more performance, you'll wake up the big core, switch over at that point, and it can be completely transparent to the OS. So looking at the software models, this cluster migration and CPU migration basically takes advantage of that OS power management that's going on in the DVFS driver and makes a switch to the big processor based on the sampled load. So that's a fairly straightforward way to deal with this. The OS doesn't need to have any kind of load balancing modifications or changes in the kernel scheduler. We're just modifying the power management frameworks to be able to deal with that. CPU migration is a relatively new development that we've come across or really been focusing on since we launched Big Little. And so in our Linaro open source consortium that we work closely together with, they've reached their first release milestone on CPU migration. And this approach is fundamentally the same as cluster migration, except at a finer granularity. So in cluster migration, I sample the load for an entire cluster, and if I need more performance, I switch everything over to the big cluster. In CPU migration, if you look at Linux today, there are already per-core load tracking mechanisms in place, and we just tap into those and look on a core-by-core basis, and we decide, okay, if I've got this one core that needs to switch, then I can wake up a big cluster and switch its context over to a big CPU that's available. The second core may not have a higher performance requirement. In fact, this is fairly characteristic of the types of workloads we've measured. There's a lot of unbalanced workloads in mobile where you have one dominant thread like the web browser render thread and a lot of background OS level activity that doesn't need the performance of a big core. And if you can't pack it all into one CPU, from a scheduling standpoint, that might be tough. It may be advantageous to run the big thread on a big CPU and keep the small threads on a smaller set of CPUs. So that is more cleanly enabled in a CPU migration case. And kind of the last case that we're working towards, this one is the software mode that's still in development, is Big Little MP. And this is the full heterogeneous multiprocessing case where the OS is fully aware of the big cluster and the little cluster and aware of the performance capabilities of each. And what it does is it assigns threads dynamically to the appropriate CPU. So it keeps track of thread load history and looks at a thread and determines, hey, this is typically something that needs to run on a big processor and can benefit from a higher performance CPU. So it'll match that thread to the A15. It'll look at background threads and put them here. And the key difference, I think, in Big Little MP is that both can be awake at the same time. In the other modes, you're switching back and forth. So you can't have A15 and A7 running at the same time. But this Big Little MP can kind of enable a smart quad-core kind of operation where you have, let's say, 2 A15s and 2 A7s running at the same time, 4 cores, that might match the performance needs of 4 running threads better than 4 identically sized cores. And from a power standpoint, if you can run something on an A7, you're always better off in terms of energy savings. If you can fit something on A7, run it there. So in terms of how these get deployed, you can build the same silicon, build the same Big Little SoC and support any of these modes. So, a 2+2 Big Little SoC can support any of these software modes. What we'll likely see is CPU migration deployed first in the silicon I expect to see in the second half of this year. And then Big Little MP is actively being developed. We may not see that released into the upstream open source community until kind of middle of next year. So this may come on as a patch to Big Little SoCs that kind of bring added functionality later. But kind of stay tuned, because I know some of our silicon partners are pushing more aggressively towards this and may try to deploy it sooner. And in terms of where we are from a hardware standpoint, we have our first test silicon back of Big Little. So we have that in ARM laboratories right now in Cambridge and in Bangalore, and we're looking at the performance of each of these approaches, and we're trying to do some energy calculations to determine which one is best for which scenario, because obviously it's going to be very workload dependent which of these software approaches is going to save the most energy, or in some cases give added performance. So we're doing testing on that now, and we expect to have results probably around the time frame of the ARM TechCon conference in October. A bit more on big. LITTLE MP. So in this case, the OS actually scales across all the cores. So in the other two cases, the OS was resident probably on one cluster. In this case, the OS scales across all the cores. Any thread can run on any CPU. The OS power management will shut down unused CPUs, kind of in the way that a second core would be shut down in a dual today if it's unused. The OS scheduler has got to choose the right CPU for each thread based on what it measures. And so there's a lot of research actually going on right now on the thread load tracking. In particular, if you look at kind of performance tracking today, what we find is that the existing mechanisms do a good job of predicting when a CPU is heavily loaded, but they do a poor job of predicting when a workload is memory bound. Because if you take a memory bound workload, something that's waiting on memory accesses, and switch it to a big processor, it doesn't run any faster. It's still waiting on the same memory resource. So we're trying to, we're doing a lot of work in that area to try to identify when a workload really can take advantage of a big core, and putting a bit more detail into how it makes that decision. The one other thing I want to say though about big. LITTLE MP is that it does require more advanced scheduling and affinity support in the kernel scheduler itself. Today, the CPU migration and cluster migration don't require any modifications to the kernel scheduler. They kind of just modify the power management frameworks. Big. LITTLE MP requires some fundamental changes to the kernel scheduler to kind of be aware of big and little CPUs, have some affinity per thread so that it kind of makes an intelligent decision about which thread gets scheduled to which CPU core. We're seeing quite a lot of interest in the open source community in developing this, but it is more challenging, so we're expecting kind of deploy this middle of next year. And that's kind of an update on big. LITTLE MP. So kind of in summary, the mobile performance range is really driving us in two directions. Higher performance at the same time as more energy efficiency. And big. LITTLE as the technology directly addresses this. And ARM big. LITTLE processors, they really provide kind of a best of both worlds solution for added performance with a big core like Cortex-A15 coupled with an energy efficient core like Cortex-A7 in a way that you can almost instantaneously switch between them. So we think this is a very key technology. And we're looking forward to working with you and the rest of the ARM partnership to deploy that over the next year. So, questions?
Yeah, with the increase of the number of CPU, both performance and energy efficient are taken into consideration. How to solve the thermal issue? I mean, did the system take into the heat dispensed into?
Yeah, it's a question. So good question. So in terms of thermal, I mean, I think big. LITTLE is fundamentally designed to address this kind of an issue. If you look at a Cortex-A7, its power profile is such that a single core running flat out is under 100 milliwatts. It's very low power. So the idea is if you can spend 90% of your runtime, 95% of your runtime on a Cortex-A7 CPU, you're easily within thermal constraints, at least on the processor side. Not really talking about the GPU yet. So if you can switch to an A7, then you can certainly stay within thermal a lot better. In an A15, we think A15 running flat out, you're probably going to hit a thermal boundary running two cores. So with an A15, you probably won't be able to run sustained with both cores running, let's say, 1.2 or 1.5 gigahertz. So you're likely to throttle those back at some point. But what we find with mobile is that the workloads aren't typically flat out all the time. They're very bursty workloads. And so being able to throttle back voltage and frequency has been helping us up to now. Being able to throttle back even further with a smaller core like an A7, I think will help us even more in addressing the energy efficiency and the thermal challenge you bring up. Does that address your question? Okay, yeah, thanks.
Nope.
Other questions? Yeah.
So the big has an L2 cache, the small has an L2 cache.
Yep.
So is there a way that you will share the L2 caches and just have one L2 cache?
So in this approach, what we do is we have a separate L2 cache for the big and the little. The reason we do that is because fundamentally the A15 L2 cache has been designed for performance. The whole L2 subsystem has been designed for maximum performance. So multiple cores can look up into the L2 at the same time. It can support a larger L2 size, up to 4 megs. We're seeing some partners looking at 2 megabyte size L2 caches. It's a 16-way associativity. So everything about the A15 cache, the L2, has been designed for performance. At the same time, the A7 has been designed for energy efficiency. It's good on performance, but it's 8-way associativity. The cores have to take turns if they look up simultaneously. The way data and tagrams are accessed is really optimized more towards energy efficiency than performance. And also there's a 1 meg max on the A7 cache size. And all those trade-offs make sense for the respective cores. If I wanted to make one cache that would support both, it would be a compromise on one direction or the other. It would have to be a bit smaller, or it would have to be, and also what we see is leakage in 28 nanometer geometries and further. Carrying around a big cache all the time is a lot of leakage. So if we're able to run 95% of the time on an A7 with a smaller cache and not having to carry around a bigger one, we think that's an energy efficiency gain. There are some benefits to sharing an L2, and I know that's an approach you guys take. So, we've definitely looked at that, and we get that question all the time. Why can't we just share the L2? The answer we came up with was we'd rather have a separate L2 that was tuned, but I think one of the really cool things about the way ARM does business is that our partners try different ways to do things, and some will do a shared L2, like I know you guys are doing. Others are doing a different way where they're powered, voltage and frequency scaling individual cores, and in each processor generation, this stuff fights it out in the marketplace, and we have winners and losers. So I think we have an idea we think is best, but I don't know who's right, and I guess we'll see. But I think that's the cool thing about the way the ARM ecosystem works.